So, we are trying to find out the equation for the thrust or the expression for the thrust, and then we will calculate other performance parameter, and this is what we started with the free body diagram, and then finally what we said that we get the mass, which is the total exhaust or exit mass flow rate would be sum of the air comes in and the fuel flow rate. Okay. So, this is what we stopped. Now, we write the continuity equation. Okay. So, what we write that control volume rho E dV plus control surface rho u dot n ds 0. So, now it is a steady. So, this component would not contribute, and then we will get from this component only. Now, in the present situation or in the present case, what we will write rho E u e a e plus rho u a minus a e minus rho u a plus m dot s. So, that is m dot s, that is minus m dot f would be 0. So, across all the control surfaces, this is what we get from the continuity equation, and A here is the cross sectional area of the control volume. Okay. Now, what we have is this is the structural support where we have m dot s, this is with angle theta. M dot s is the mass flow rate of air through the side surface. Now, this is the side of CV control volume at sufficient distance or sufficiently distant. Now, from the engine, this theta is very small. So, which leads that momentum is m dot s into u. So, what we write that therefore, the control surface rho u dot n ds, this is in the momentum equation, it is m dot u e plus m dot u plus rho u a e minus e minus m dot u minus rho u a minus a I into u. So, this is a component which we get in the steady momentum equation. Now, we using 2, it follows that. So, we put equation 2, that is what we get from the continuity, this guy into this one, and once you do the math what we will get, that the control surface rho u dot n ds is m dot u e minus m dot a u. So, once we get this, now putting back in equation 1. So, now putting back in equation 1, it becomes T equals to m dot e u e minus m dot a u plus p e minus p a e. So, that is what we get. This is equation 3. So, this is what also one can say, this is the thrust of a turbojet. Okay. So, you can get finally the expression for the thrust of a turbojet engine. Now, we consider the fuel air ratio now. Fuel air ratio, which is usually represented with F, which is m dot F by m dot A. Now, when we use this, then what we get, we have also obtained that m dot E is m dot A plus m dot F. So, this is m dot A into 1 plus F using the fuel air ratio. Now, using this one in the thrust equation, the thrust equation becomes little bit m dot A into 1 plus F u e minus u plus p e minus p a into a e. So, you can, so given a fuel air ratio. So, these are the parameters. They are important because when engine specification, if you look at the engine specification from any book or these things, I mean like the pressure ratio, speed, efficiencies, range of operation, fuel air ratio, these are given. So, that is what you can get. Now, typically for air breathing engine, in general F is very small, and the term also, that this particular term, which is P e minus P a into A, that is also small, very small, or almost. This is the situation with the, in the case of subsonic flow through the exhaust. So, then what we can neglect this term and that term, and then finally, we can write T equals to m dot A into 1 plus F u e minus u. So, which immediately says the thrust is proportional somewhere m dot A u e minus u. So, what happens? Thrust always increases when either m dot A or u e they increases. Now, for supersonic flow, P exit is greater than P atmosphere. So, what happens that P star by P naught is 0.528. So, the P star would be 0.528 into P naught. If P is the ambient pressure, and this is the case, P is ambient pressure. So, if P star by P naught greater than P by P naught, then typically P exit would be P star. This is for converging nozzle, and if P by P naught less than 0.528 or P less than P star, this is the case when it is supersonic. So, another thing one can see that thrust is proportional to m dot A and UE. Okay. So, if let us say if UE is quite high than these things, so thrust becomes incoming mass flow rate and the exit velocity. So, this means that exhaust gases are much more energetic than incoming air. Now, that we get for the all this information when you get the. Now, we can look at the same thrust equation for turbofan. So, we will not. So, we can write the equation. We will derive all this equation also later on, but right now just to define all the different performance parameters, we just need to have the basic equation for the thrust, where m dot H plus m dot H u H minus m dot ASU plus m dot AC UC minus U. So, this is the primary component of the thrust or hot thrust. This is the secondary component of the thrust or the cold thrust. And also here the assumption is that the PEH is PEC is PA. This is atmospheric pressure, this is the pressure at the exit of the hot gas. This is now just to quickly get back to this here the picture that will give you an idea. In turbofan you have a fan and then there is a cold thrust which is by going through this bypass and rest go through the engine. So, that is what you have the hot component, cold component, and from the turbofan engine one can always get back the turbojet engines, where if you do not have this bypass, then this if you remove that out, then essentially it comes down to the same turbojet engine. But since there is a fan and there are two different components of thrust which come into. Now, we also define fuel air ratio for turbofan. Here it would be m dot F by m dot AH, because this is the portion of the air goes through the core, and another parameter which we call the beta, this is called bypass ratio, and that is defined the percentage of the air which passes through the cold. So, using this we rewrite the equation for the thrust, which is m dot a 1 plus f u E h minus u plus m dot a c u c minus u. So, this what we get for the turbojet. I mean schematically one can see, okay, this is the nozzle, then you have this. Now, here are the fan sitting there, then it goes through like this. So, you have this component, then you have the combustion chamber, then so you get turbine, so it sort of passes through the. So, that is what U comes in. This is the cold and this is where the hot, this is combustion chamber, compressor, and then finally this is U E h and this is U E c. Here you have m dot f. So, these are the. Now, similarly, if you have a rocket engine, like let us say you have this so you get the exit here, A E U E P E U P at this. So, the thrust equation would be T dot T equals to m dot U E plus P E minus P A A E. So, that is sort of. Now, here with m dot equals to rho E U E A E, we can write where T equals to m into C. C is the effective rocket engine exhaust velocity, which is m dot U E plus P E minus A E by m dot E. So, this is effective one, then you can write the thrust equation like that. So, once you see this, one can identify the things which are important, like we can see the factors which are affecting thrust. Okay. So, obviously, any of these turbojet or turbofan or this engine, so thrust depends on inlet and outlet mass flow rate, that is there, fuel air ratio, flight speed or U, exhaust speed, that is U E, and then exhaust pressure, ambient pressure. So, all these are important factor. So, it looks like they are pretty simple to identify these factors which are listed here, but each of these parameters what I mean has been listed here, they depend on multiple or several factors. For example, one can take let us say the inlet air flow rate, that inlet flow rate of air or inlet air flow rate influencing both the momentum thrust and the momentum drag. Momentum thrust and momentum drag is dependent on several variables including flight speed, ambient temperature, pressure, humidity, altitude, rotational speed of the compressor. So, these are this affect momentum component of thrust, and momentum drag depends on so many things like flight speed u, then pressure, humidity and so on other factors. Similarly, the outlet gas mass flow rate is dependent on fuel added, like how much fuel is added there, air bleed, water injections. Then the pressure thrust term also depends on turbine inlet temperature, flight altitude, nozzle outlet area, and the momentum thrust also depends on jet velocity. So, these are multiple factors which affects. So, some of the important factors like let us say jet nozzle, how. So, you can see that pressure thrust has finite values for choked nozzle, where the exit pressure is greater than the ambient pressure, that means P A greater than P A. So, nozzles are either could be convergence or divergent, it could be either convergent type or could be convergent divergent type. Now, only convergent type can be choked. For choked convergent nozzle, the pressure thrust depends on both the area of the exhaust nozzle and also on the difference between the exit and ambient pressure. Further, the exhaust speed is equal to the sonic speed, which is mainly influenced by the exhaust gas temperature. Now, if a convergent nozzle is unchoked, so then the jet velocity will attain subsonic values, and for CD nozzle the jet speed may attain supersonic values. So, this you will see this how these things happen. So, when we will talk about these nozzles and all these things in the later half of the lecture, but the interested person may look at the compressible flow book at this for the time being. Now, air speed, this also sometimes depends on the approach speeds, also is equal to the flight speed in the thrust force. Such a parameter has a direct impact on the net thrust. So, there is a direct impact on thrust. If the exhaust gas velocity is constant and the air velocity is increased, then the difference between let us say 1 plus F into UE minus UE, this also decreases, which means the thrust also decreases. So, if the air mass flow rate and the fuel to air ratio are assumed constant, then the linear increase in the net thrust is decrease in the net thrust is enhanced. Okay. So, the air mass flow rate. So, this is m dot A. This is a significant parameter in thrust. It depends on ambient temperature or air temperature, or rather temperature, pressure, and sometimes both together with the density. In free air, if there is a rise in temperature, if temperature is increasing, which will decrease the density, and the mass flow rate will be also inversely proportional with the air temperature. Okay. So, on the other hand, the ambient pressure, an increase in pressure, if pressure increases of a free air, also it increases its density. So, that means the thrust also increases. Okay. So, one can quickly see what happens if, let us say, this is my thrust and this is P A, this is how it increases. If this is T ambient and this is my thrust, this is how it decreases. So, the air mass flow rate though has important impact on the thrust, but this also depends on pressure and temperature which are at the ambient and how that depends. Then the altitude. So, this is another, already during discussion on atmosphere we have already talked about this, that altitude has direct impact, because in the altitude the pressure, temperature, that varies with altitude. Okay. So, once pressure, temperature varies, then so with the height, like one can write that how these things changes. For temperature with the altitude, it changes like 0.0065 into z, where z is the height or altitude, and pressure changes in bar 1.01325 minus 0.0000112 into z plus 3.8 e to the power minus 9 into z. So, after 11 kilometer the temperature stops falling, but the pressure continues to drop steadily with increasing in the altitude. So, consequently what happens above this above 11 kilometer, the thrust will drop off most rapidly. So, after 11 kilometer thrust drops off rapidly. So, this makes around this 11 kilometer is an optimum altitude for long range cruising normal speed, just prior to rapidly increase of the effect of the altitude of the thrust. So, one can, in one word, one can conclude that this thrust is really a function of density, because when you change the altitude, pressure changes, temperature changes, so density changes, obviously mass flow rate changes, and the thrust is going to be affected. So, just a schematic of that, how it can vary, like thrust, and this is altitude. So, you can see there is a linear variation and then there is a drop of thrust. So, this probably around roughly 11 kilometer. So, this is how these factors affect, and there are some more other factors also, and we will continue this discussion in the next lecture.